Hey, this is Frank Kane from Sundog Education. Ever wonder how all those viral apps on your phone work that do face swapping and things like that? Well, they use a technique called Generative Models. If you've got an hour, I've got this excerpt from my larger course on machine learning that tells you exactly how they work with Variational Auto-Encoders and Generative Adversarial Networks, or GANs. So dive in with me and we'll write some code together and see how they work. All right, it's time to get into the fun part of this course. We're going to talk about generative modeling. This is the technology behind all those viral apps that let you swap faces around and age people and stuff like that. Also, the technology behind deep fakes, kind of a poster child of the ethics discussion we had earlier in the course, but I'll spare you my rant on that for now. Before we can talk about generative adversarial networks, though, which is the tech behind all that stuff, we need to talk about variational autoencoders, which is the underpinning of generative adversarial networks. So let's dive into VAEs first. Before we talk about variational autoencoders, let's first talk about autoencoders in general. This is kind of a diagram of how they work. So an encoder learns how to reduce input down to its latent features. So that's kind of the left side of this diagram here, the yellow part there. So basically we take an input, which is often an image, and by using convolution, just like we saw in convolutional neural networks, we distill that down to some sort of representation of the latent features or latent vectors of that input signal. So our encoder there looks a lot like a CNN. It's using convolutional layers and max pooling and all that stuff to sort of distill down the patterns in the input that we're training it with down to these latent vectors that we're representing here as the blue Z box in the center there. So nothing really too new there. On the other side, though, we have the decoder, which is basically the inverse of the encoder. So it's being trained on how to reconstruct complete images or complete data, more generally, from those latent vectors in the Z box there. So by using transpose convolutions and max depooling and things like that, it learns how to take those latent vectors and reconstruct them into a full complete image or a full complete data set. So while we're training this, the objective is to try to get the input and the reconstructed input to be as similar as possible. That's what we're trying to optimize for there. So x should be about equal to x prime, where x is the original input images that we're training it on, x prime are the generated reconstructed images based on those latent factors, those latent vectors that we've learned through the training process. So pretty interesting stuff. Now the system as a whole is trained such that the original input fed into the encoder is as close as possible to the reconstructed data generated by the decoder. What I just said, but let me try to make that a little bit more real with an example, right? Let's say that we're training this on pictures of shoes, all right, just to pick something out of the blue there. So the encoder would distill that down into sort of the essence of what makes a different kind of shoe. And it's not going to be thinking about it in these terms, it's just a neural network, right? But what those latent vectors might ultimately represent is this thing kind of fits the pattern of a sandal, and this other thing kind of fits the pattern of a sneaker, and this other thing kind of fits the pattern of a boot that I've learned. It doesn't know how to label them or to call them those things, but that's what it might learn in those latent vectors in the Z box in the middle there. And the decoder will learn how to take that and reconstruct a complete image of a boot or a sandal or a sneaker based on that latent vector there. And it could be more to it than just a classification, right? I mean, a very simple latent vector would just be a classification of what kind of shoe is this, but we can have more information in there that's more nuanced. And that's kind of the beauty of the system. It's a little bit more flexible. And once we've trained the whole system, we can actually throw the encoder away because we just use it for training the decoder, really. So if you want to just generate synthetic images of different kinds of shoes, you could use the decoder to do that. And the idea is, you can generate a bunch of synthetic generated pictures of sandals or sneakers or whatever it is at random if you wanted to. And that's kind of where the underpinnings of all these sort of fabricated faces that you see on viral apps comes from. So there's a lot of applications to this. I mean, going back to the ethics discussion, nobody really intended this to be used for deepfakes or deceiving people, right? The original goal was actually for compression. So you can think of this as sort of a noiseless way of compressing data down. So if you want to have a really clean way of saying, I just want to have a picture of a sandal, here's a way to do that with just, basically a few bytes of information potentially, where it learns how to reconstruct that without any noise. Also, it can be applied to dimensionality reduction, obviously. Kind of the same thing as compression. We're taking that higher dimensional input and boiling it down to those latent vectors there instead, to a lower dimensional representation. It also has applications in search. So we could use that to sort of distill a corpus of text data down to its relevant search terms. Denoising, the decoder can be used to reconstruct an image that has no noise in it based on an image that does have noise in it. That's another good application of it. I use that in Photoshop all the time, actually. Or colorization is also a cool application. Maybe this thing can be trained to recognize that this picture of a person looks like he's wearing a pair of jeans in this black and white image. And based on the shape and the shade of gray in that image, we think it's a pair of jeans, and maybe I should color it blue because most jeans are blue. So, again, it's not thinking about it in those terms, but those are the labels that we might attach to what's going on under the hood there. So again, the trick for doing this in the decoder is to use a transpose convolution instead of a convolution. So instead of conv2D layers, we're using conv2D transpose layers to reconstruct images from those latent features that we talked about. So it's going to be learning all the weights used to create a new image with new pixels from a lower dimensional representation. And again, it can be used on more than just images, like we talked about. Search and text information is another application, but images are kind of the easiest example to wrap your head around here. So with a transpose convolution, we're not distilling things down or shrinking images down. We're actually expanding them into their original form. We're trying to. You'll often see it used with a stride of 2. I've also seen some decoders where they sort of intersperse strides of 1 and 2 at different layers if you need more complexity, but you'll probably see a stride of 2 in there somewhere. And again, if you're we're going to be using max unpooling instead of max pooling, like we talked about when we talked about convolutional neural networks. So think of the decoder roughly as a CNN that works backwards. It's kind of a good way to wrap your head around it. So let's talk specifically about variational autoencoders. What do we mean by that? So in a variational autoencoder, those latent vectors are probability distributions. And this is a way that we might graph those probability distributions for a given, given set of categories or what have you. So we represent those probability distributions by the mean and variance of Gaussian normal distributions. So a variational autoencoder is specifically using Gaussian normal distributions and the properties of those distributions as its latent vectors that it learns over time. Mathematically, we can express it like this. The input data x is expressed as a probability of z given x, where z are those latent vectors, and then we can reconstruct z using the probability of x given z. So flipping that back on its head to reconstruct the original image. And this is the inspiration of generative adversarial networks, or GANs. So we're getting there soon. We'll see that GANs are just another spin on variational autoencoders, where it's more general than using Gaussian normal distributions. One thing that you're going to see in the code that we should talk about is something called the reparameterization trick. I'm not going to say that again because that's a tongue twister. So one mathematical problem with the idea of VAEs is that the probability distribution that we're calling Z can't be differentiated. Anytime you have randomness in the equation there, these random distributions, that throws a wrench into the calculus, right? And as you might recall from when we talked about training neural networks, we need to use the derivatives of this system for backpropagation and the actual learning to work, right? So the trick we use to get around that is by converting the random sampling in Z to a deterministic form. So mathematically, we might call that Z equals mu plus sigma times epsilon. The specific Greek letters you use don't matter. We're actually using different ones on the diagram here. But the idea is that we're introducing this new epsilon term, or whatever you want to call it, where the randomness gets moved off to. So epsilon is the random variable from the standard normal distribution here. And by pushing that out into its own term, that pushes the random step out of the network as an input. And then we can have a connected graph again that we can actually differentiate and actually do training on and backpropagation. So I'm not going to get into the math of that too much. I just want you to know what that is. Also, in the subject of things you just need to know what they are is Kullback-Leibler divergence, or KL divergence for short. This solves the problem of measuring the distance between two probability distributions. So what we need, as we're training, to measure the distance between the probability distributions of our original data and the reconstructed data. We want those to be as close as possible, right? And one way to measure that is KL divergence. Sometimes they call it the Earth mover distance because of an analogy used of how much Earth would you need to move to transform the United States into the shape of the United Kingdom. I think that's the actual example used. But a simpler way to think about it is this diagram here. Let's say we have a shape of 3 stacks of 3 blocks. It's basically how many blocks do I have to move to get it to look like 9 stacks of 1 block, right? So it's just how much information do I need to move around to make these two distributions, these 2D graphs, line up with each other. Mathematically, it looks like this: the sum of p of x times the log of p of x over q of x, which is equivalent mathematically to the cross entropy of p and q minus the entropy of p. So we sometimes also call this relative entropy. And as you might recall, entropy is a really common loss function, so it means we can use this as a loss function while we're training our variational autoencoder. And further, we can decompose that as this function here. I'm not going to get into the mathematical derivation of that, but when you see that function, this is where it's coming from. That is the Kullback-Leibler loss function here, expressed as you might see it in TensorFlow. So with that, let's dive into a notebook and see how VAEs actually work. All right, let's see variational autoencoders in action. And to put a little bit of twist on things, we're not going to use the traditional MNIST dataset of handwritten numbers. We're going to use the fashion MNIST dataset, which is actually little pictures of pieces of clothes. So mixing it up a little bit here. What we're going to try to do is train our VAE to generate pictures of clothing. So let's see how it works. All right, so let's dive in here. Open up the Variational Auto-Encoders notebook from the course materials if you'd like to follow along. If you do want to follow along, though, it's pretty important that you have a GPU available, that you have TensorFlow GPU installed. Otherwise, you're going to find that this takes a really long time to train. So if you don't, just head over to this link here at tensorflow.org/install/GPU, and that will walk you through what you need. You will need an NVIDIA graphics card, and you'll probably need to go to the NVIDIA developer website and sign up to get the CUDNN library installed as well. But this walks you through what you need to do if you do want to follow along and you don't have TensorFlow GPU installed. If you don't know if you have GPU support already, that's what this first block checks. So let's go ahead and Shift-Enter in here. And it's just going to list how many GPUs I have access to from TensorFlow. It's also going to load up the TensorFlow library itself, so that's going to take a little bit of extra time. I can hear my hard drive chugging away as it loads up TensorFlow. All right, the chugging is slowing down. We have 1 GPU available. That's enough. But if it says 0, again, you're probably going to want to stop and either go install TensorFlow GPU or just watch the video without following along, because otherwise both VAEs and GANs will take a long time to train. All right, we're also going to set a consistent random seed so I can get somewhat consistent results out of this notebook and don't have any nasty surprises. This is pretty complicated. It's harder than you might think to have a consistent random seed and to get consistent results. And that's because we're using a GPU, so we're doing a bunch of training in parallel, and getting consistent results out of that when you're dealing with randomly generated initial conditions and various randomness within the model itself even, that can get a little bit dicey. Even with all of this that we're doing here, we're not going to get perfectly consistent results, but it will at least be close. So let's go ahead and Shift-Enter on that as well. All right, let's talk about that fashion MNIST data set a little bit. So like I said, it's like the MNIST data set, the one that we've been using before, where it's just handwritten digits 0 through 9, right? The difference is that instead of numbers, we're looking at pictures of clothes. So a little bit interesting. And the various classes that we have available to us are t-shirts, trousers, and pullovers. I'm guessing this came from the UK or something. That's pants and sweaters where I come from. Dresses, coats, sandals, shirts, sneakers, bags, and ankle boots. So you can see that example I talked about in the slides of different kinds of shoes was not theoretical. We're really going to be looking at sandals, sneakers, and boots independently here. So let's start by importing our data in and making sure that we understand the dimensionality of it. So all we're going to do here is load up the fashion MNIST dataset, which conveniently is built into Keras.datasets already for us. We'll load that up, and we'll just check that everything's as we expect. 60,000 training images and 10,000 test images. Each one is 28 by 28 grayscale image. All right, Shift-Enter. And nothing's complaining, so everything is as we expect. And it's always a good idea to take a look at the data, get a feel for it before you start messing around with it. So what we're going to do here is plot what this looks like in a 9x9 grid. We'll take 9 samples at random out of our 60,000 training set and plot each one using grayscale. And let's see what we get. Just plucking out 9 at random. So you can see we've got what looks like a, I guess that would be called a sandal, a handbag, looks like a dress, some pants or trousers as they call it. Ankle boot, I guess, Honestly, I'm not sure what that is. I think that's a handbag. So you can see, the data is not the greatest to begin with, but that's what makes this challenging and interesting, right? But they're pretty, except for that thing. I'm not sure what that is. Everything else is pretty recognizable as a piece of clothing. All right, so the first thing we need to do is pre-process our data. First thing we're going to do is combine our training and test data together. Why? Because this is not a classification problem. I'm not trying to figure out, is this a boot, is this a pair of pants? I'm trying to create a system that can generate pictures of clothes in general. So because I'm not actually trying to test my ability to classify these things, that test data set with that label data that tells me if I classified it right isn't really useful for this problem. So instead, I'm just going to use it for extra training data. So the first thing we're going to do is concatenate the training data set and the test data set together into a single data set called creatively dataset. I'm also going to add an extra dimension to that data set because our convolutional layers expect 3 channels of input, not just 2. I'm also going to convert that to floating point data and normalize that to 0 to 1. So the raw data is just going to be integer data from 0 to 255, representing how bright that pixel is. This actually transforms that to a floating point number between 0 and 1 because the sigmoid activation values in our model are between 0 and 1. So we're just sort of massaging the data here to fit the input of our convolutional layers better. Shift-Enter to run that. All right, so now things get interesting. First thing we're going to set up is our sampling layer here. And this is where that reparameterization trick, hey, I actually said it right, comes into play here. So remember, we need to move that random component out into an epsilon term while retaining mu and sigma, the mean and variance of our data coming in here. Actually, we're going to be using the log of the variance as we come into here, as you'll see shortly. So our sampling layer is going to be this custom layer, and it will take in the inputs of the mean and log variance. It will then extract what the batch size is by looking at the first dimension of the z-mean input coming in, and the dimensionality of that data by looking at the second dimension. We then compute epsilon, that is the random term we talked about in the slides. It's just a normalized random number of that shape that we expect to match up what we're getting in for the z-mean data that's coming in. So we're creating a bunch of epsilon random numbers in the size of whatever the batch size is times the number of dimensions that we have. And what we return is just mu plus sigma times epsilon. It's a little bit more complicated because, again, we're using the log of the variance here for training purposes later on. So to convert that back to an actual variance, we'd have to take the exponential of that of 0.5 times the log of the variance. So some basic algebra there. But fundamentally, this is returning the reparameterization trick we talked of z equals mu plus sigma times epsilon. All right, next let's actually create our encoder model. Let's run that before we forget. Shift-Enter. We're going to be using the Keras functional APIs to build this because it's a little bit complicated, or more complicated than usual. It's not really that hard. All right, so we're going to have this build encoder function. Its job is to return a Keras model for the encoder, part of our larger model. Let's start by setting up a sequential model that consists of 2 conv2d layers. We're going to start off with a 128 number of filters going down to 64. We'll then flatten that out and dump it into a dense layer of 256 neurons at the end. And strata 2, like we talked about. Again, these are kind of hyperparameters. The topology of this, the exact number of filters that you use at each convolution layer, those are things you can play with. The number of convolution layers you have, what the strides are. So I've seen people, like I said, leave strides of 1 and 2 in there for more complexity if they need more neurons in their model for doing a more complex task. Again, it's a lot of trial and error to get this right. So it's kind of the dirty little secret of deep learning. A lot of it's just experimentation and trying different things until you see what works the best. All right, so we're going to pass in our inputs through that convolutional block. So we just call that sequential model that we just set up with the encoder inputs that come into this function, this build encoder function. Next, we'll create a dedicated layer to learn the mean and the variance in parallel. So we're setting up 2 different layers here. One's going to be a dense layer of the dimensionality that we pass in as a parameter to build encoder. Again, another hyperparameter we can play with. One's going to be dedicated to learning the means, and ones will be dedicated to learning the logs of the variances as we go. Okay. We then call sampling layer with the z-mean and z-log var that we just set up there. Again, that's dumping it into here where we apply that reparameterization trick to combine it all together. All right. And we return finally the actual Keras model that's composed of it all. We pass in the model with the encoder inputs, z-mean, z-log var, and the latent vectors there is z. All right, a little note here in the comments here too. Note that z-mean and z-log-var are not the final output of this encoder, but we will feed that into the KL divergence loss in a little bit. Now that we have our function to build the encoder, let's actually use it. We'll set up our input layer here of 28 by 28 by 1. So again, our input images from Fashion MNIST are 28 by 28 with one color channel, just grayscale. We'll call that encoder inputs. Pass it into build encoder with latent dimensions of just 2 and the inputs that we just loaded up. And we'll print out the summary just to do a sanity check. Shift enter, see what we get. There we go. All right, looks reasonable to me. Moving on. Now we need to also implement our decoder. So again, it's kind of the inverse of what we just did. We're just going to be using conv2d transpose instead of conv2d, because instead of trying to reduce these images down to their latent vectors, we're going to be expanding them from their latent vectors to an image. So we're kind of going backwards here. The model here is going to start off with a dense layer. We're going to reshape that to 7 by 7 by 64. And then we'll set up 3 conv2d transpose layers, starting at 128 filters down to 64, and then finally down to a single image that we should finish up with. A little bit confusing potentially here because, you might say to yourself, why are we going down in size here when we're trying to make a bigger image? But, this is the dimensionality of the number of filters we're applying here and not the size of the image that we're producing. So keep that in mind. All right, we'll return the model. Again, just passing in that model that we called L1 here with the latent inputs being passed into build decoder, and we'll call it decoder. And then we'll actually build it by loading up the input shape there. Again, the shape coming in is just 2 because we created the encoder with a dimensionality of 2 just above us. We'll then call build decoder there and print out the summary of the decoder model. Shift enter. Yep, looks reasonable to me. All right, next we need to set up our loss functions. Yes, plural. There are 2 of them, and I didn't really make that explicit in the slides, I don't think, but it's definitely explicit here. So there are 2 loss functions here. One is the reconstruction loss, and that's what's going to be penalizing images that are not similar to the original images. So remember, our overall goal is for our decoder to generate images that are as close as possible to the original images that were fed into the autoencoder. And this is the loss function that measures that. It's just using binary cross entropy on the original data fed in and the reconstructed data that was generated by our decoder. Okay, pretty simple stuff there. Shift enter. And then we're also going to measure the KL divergence loss here as well. And this we talked about in depth in the slides about what that's all about. So I'm not going to go over it again. But, we did talk about where all these formulas came from there. Again, this is looking at the distance between the probability distributions on both sides. So we're looking at the probability distribution of the original data versus the probability distribution generated from the generated data. And we want those, again, to be as close as possible. And we're measuring that with the KL divergence loss function here. So let's go ahead and define that as well. Shift enter. And, well, we need to have a overall loss function at the end of the day. You can't really have 2 loss functions at the same time. So that's what this next block does. It calculates the total loss as a function of both the reconstruction loss, which again is just measuring how similar the original and reconstructed images are to each other, and the KL divergence loss, which again is measuring how close the probability distributions of each image is. Now we need to combine them together somehow. The obvious thing would be to just take the mean of the 2, but it turns out that weighting that is also another important hyperparameter that needs to be tuned. So you can see we're getting pretty deep into the number of hyperparameters that need tuning in this model in the variational autoencoder, and that's why it's so difficult to get these things trained well. Now, this KL weight is basically what we're calling that parameter, 3.0. Basically, we're going to be weighting the KL divergence loss by that number. And that is a very important parameter for affecting how good the final results are, it turns out. So I've done some experimenting already and settled on a number of 3, but maybe you can do better. Maybe a different weight will actually produce better results for you. Let's go ahead and shift enter. Again, all we're doing here is taking the reconstruction loss, calling that loss 1, the KL divergence loss, calling that loss 2, and we're returning both the individual losses so we can keep track of them as we train, but the final total loss that we're actually going to be optimizing on is going to be the reconstruction loss plus the weight of 3 times the KL divergence loss. That's how we're combining them together into the overall loss function. All right, moving on. So because we have a custom loss function, we kind of have to make our own custom model that uses it. Most of this code looks like a lot of code, but most of it's just keeping track of those different loss functions so we can graph them and visualize them later on. We're going to create a VAE model here that derives from keras.model, so it's just a custom model. We're going to create our own little constructor here that just sets up a total loss tracker, a CE loss tracker, and a KL loss tracker. So this is just going to be used to keep track of the total loss, that combined loss that we talked about, that includes that weight on the KL loss, the reconstruction loss, which here is called CE loss, and the KL loss, which is called KL loss. And we declare those as all being observable here in this block of code. And here's where we get to the actual meat of our actual model here by overriding the train step function. So we use a gradient tape here in Tensorflow to actually explicitly define how the training works. For the forward path, we just call self.encoder with the data coming in, and that returns back, as we saw above, the z-mean, the z-log-var, and the z itself. We then construct the reconstructed image by calling self.decoder, and that will give us back our reconstructed images. So encoder, again, is running our encoder model to boil those images down to that probability distribution z, and we're also keeping track of the means and log variances independently here as well. And then the decoder is called with that resulting probability distribution z to try to reconstruct that image, and we're calling that reconstruction. We then calculate the total loss between the two. And again, calc total loss is looking at both the reconstruction loss and the KL divergence loss, and we're going to keep track of them both independently so we can view them, and finally just look at the total loss between the two. For the actual training itself, that happens in the back propagation phase, right? If you remember how neural networks just work in general. So what we're going to do here is just calculate the gradients here based on the trainable weights that we set up. And we will apply gradients by just zipping together those gradients and the trainable weights, and we'll optimize on those trainable weights. What ties this all together is using that total loss here that came from calc total loss to actually, bake that into how the back propagation works. So that's really where we're incorporating our custom loss function into how this model is trained. Again, we're going to keep track of all those individual loss functions, both the KL loss, the reconstruction loss, and the total loss function that combines the two independently, so we can graph them all independently as well. And we return all three just so that we can keep track of them. All right, Shift-Enter to set that up. Shouldn't take long, but this next block will take a long time. Here we're actually going to do the training. So we're going to set up our VAE model, passing in our encoder model and our decoder model. The VAE model puts them all together. We'll compile that model using the Atom optimizer. And this learning rate is yet another hyperparameter that needs to be tuned. This is one that I had to tweak quite a bit while experimenting with this notebook myself. And finally, we'll call fit to actually do the training itself. We're going to use 32 epochs of training and a batch size of 128. Yet more hyperparameters that need to be tuned. In general, more epochs is better, but if you're finding that the model's not stable, which is pretty common, more might not be better. So again, experimentation is needed to see how many epochs you really need once you get everything else right to get good results, and what batch size makes sense. So very easy to overfit here, very easy for getting stuck in a local minima and not getting out of it. That's also something that happens a lot when you're training these things. So I'm going to go ahead and kick this off. Even with the GPU, it's going to take a while. So what I'm going to do is, through the magic of video editing, just pause this recording and come back when it's done. Let's let the first epoch run at least, though, before I do that. I think the act of recording this video was actually competing for resources on my GPU. There it goes. So you can see here that we can watch the reconstruction loss, the KL loss, and the total loss coming together there. And you can kind of see why we had to weight that KL loss a bit. Those are much smaller numbers, at least at first, compared to the reconstruction loss. So the reconstruction loss is really dominating the trading right now, and its contribution to the total loss. And as we go over time, we should see that reconstruction loss getting smaller and smaller. And as that happens, the KL loss will be more of a factor as it trains further on. So really, the more epochs you have, the better it gets, and the more that KL loss will come into play. All right, again, as I said, I'm just going to pause this and come back when it's done. All right, that took about 10 minutes even with a GPU, but our training has finally wrapped up. And we can kind of eyeball what happened here by looking at the loss functions reported over time. You can see we started off with a total loss of 313 and got down to about 266 here. You can definitely see just by eyeballing it that it was really kind of reaching a point of diminishing returns here, and was actually really struggling by the time we got to 31. It actually went back up at 32. So 266 seems to be about as good as we were able to get. Whether that's because it found the best solution or because it got stuck in a local minima, well, I guess we'll find out. You can also see that the reconstruction loss is really much larger than the KL loss. So, that was really playing a much larger role than KL loss as we went. So it might make sense to experiment with using a larger weight on the KL loss if you have time. You might want to play around with that a little bit. And also, it's possible we got stuck in a local minima here. I guess we'll see how good the results are in a moment here. But if so, experimenting with the batch size might be a good way to try to get out of that minima more easily. Anyhow, we can kind of eyeball what's going on here, but let's plot it because we went through all this trouble of actually keeping track of all those numbers. So, and here we can actually see plotted the total loss, the reconstruction loss, and the KL loss. Again, KL loss being a much smaller value. Hard to see what's going on there. And you can see that, after just a couple of epochs here, it kind of was really struggling to improve and decrease that loss function further. This KL loss is hard to see because it's so small in comparison, so let's zoom in and just look at the KL loss independently here. You can see that was actually getting worse over time, so that's kind of interesting, right? So, definitely not the direction you want to be going for a loss function, but at least it wasn't like, going up exponentially. It at least started to level out. So this might suggest that training for even more epochs may have been beneficial because, we were starting to get to a point where we couldn't really squeeze anything more out of the reconstruction loss, but there are improvements to be made on KL loss. So if we went further in training, we might have seen that KL loss start to drop as it started to basically turn to that for making the model a bit better. All right, so let's see what kind of results we got here. So we're just going to randomly pick a mu of 1 and a variance, a sigma of 2. And see what we get out. So again, the idea here is to sort of, now that we've trained the model, we can throw out the encoder and just use the decoder to construct synthetic images. So let's see what a probability distribution of 1 and 2 gives us. So we're just going to call the decoder, ask it to predict, actually generate an image based on the input of 1, 2. And again, that corresponds to our mean and variance. We'll just plot that as a grayscale image, 28 by 28, and see what we get back from it. Hey, that's pretty cool. So we have synthetically created, apparently, a pair of pants. That looks reasonable, right? So, hey, I'm pretty happy with that. That's the training worked. Awesome. Let's go further. So let's actually generate 256 images now entirely at random. What we're going to do is just guess at the z distribution each time with a random mu and sigma. And, don't worry about guessing here. We can actually get back the actual mu and sigma associated with each category systematically, or at least approximate it if we want to. But for now, let's just generate 256 random images. So we're just going to guess with random normal distributions for both the mu and sigma at a scale of 4 and see what we get back. So let's construct 256 of those random distributions, call the decoder on that entire array of input values, and plot them all out one at a time as, again, 28 by 28 grayscale images in a 16 by 16 grid. Boop. And there we have it, 256 synthetically generated images of clothes. And these are actually pretty darn good. Wow, I'm happy with that. So yeah, this isn't really much worse than the source imagery, really. So I think we got lucky that time, and we actually hit on a real solution here during training. Yeah, I see, sweaters, I see shirts, I see pants, I see sandals, I see ankle boots. We really got lucky on this one. So good results, I'd say, so far. So that's all well and good. We can generate random images of pieces of clothes, but what if I want to generate a specific kind of a piece of clothes? How do I do that? What if I just want to draw a pair of sandals or something, right? Well, one way to go about it would be to just run a known case of a given category through the encoder, observe the mu and sigma that came back from the encoder for that image, and send that back into the decoder to try to get a similar image to the one that you just threw to the encoder, right? It's not perfect. It's not totally a concrete way of going about this. There is something called conditional variational autoencoders if you want a more concrete approach to doing this, but this is a reasonable way to do it. Take a picture of a shirt and put it to the decoder and say, I want a picture that looks like this, and you'll probably get a shirt back. So let's just randomly pick image number 1280, whatever it is, in our training data set. I'm going to go ahead and expand that into 3 dimensions, and like the encoder expects it to be, and go ahead and convert that to a floating point value between 0 and 1. I'm going to print out the shape of that just to double check it, send it to our encoder, ask it to predict what that probability distribution will end up being for that specific image. And then we'll pass that probability distribution into our decoder to get back a synthesized image. And we'll see what exactly that probability distribution is by just typing in Z at the end there to print it out. Shift Enter. All right, so we can verify that we got a 28 by 28 by 1 image there, just like we expected. And what came back from the encoder was a probability distribution with a mean of negative 0.427 and a variance of 1.259. All right, cool. So let's go ahead and take that distribution and see what it gives us. So we already called the decoder on that and save the result in synth. Let's just visualize what's in synth. And we'll visualize that alongside the original image as well. So we'll set up a plot here. We're going to plot the training image that we fed into the encoder to get a thing to be similar to, and then we'll spit back that synthesized image that should be similar to it. So Shift Enter. And yeah, sure enough, turns out image number 1280 is a dress, and we got back a shape that looks kind of like a dress. So by doing this, we were able to synthesize a specific category of clothes. So that's one way to go about using that VAE. Another thing you can use VAEs for is basically unsupervised learning. So let's visualize what those probability distributions look up if we color them by the actual known classifications. So I'm going to feed in the labels from our training and test data here to this graph and plot the means and variances across our entire data set there from the encoder. So we're going to throw the entire data set into our encoder, plot the resulting probability distributions, and color those based on their known categories. Got it? Let's go ahead and Shift Enter and see what that looks like. And there you have it. So you can see that we're seeing those clusters. We can actually visualize that there are distinct probability distributions for these different kinds of clothes. So, I don't know what these different colors represent. Maybe the purple ones are pants and maybe the green ones are dresses. I don't know. But you can think of this as a form of unsupervised learning where those different distinct areas of probability distributions probably correspond to classifications, different kinds of things in our source data. So if I didn't know what those labels were ahead of time, maybe I could infer them by digging into what these different probability distributions tie back to in our source data. So another possible application of VAEs, unsupervised learning of categories. But the more interesting application is in generating synthetic images, and next we'll build on that with GANs. All right, now that we have variational autoencoders under our belt, let's talk about generative adversarial networks. It's a similar idea, but different, different enough that it's its own thing. Yes, this is the tech behind deepfakes and all those viral face-swapping apps and aging apps you've seen before. For example, this is a picture of someone who doesn't exist. This is the output of a generative adversarial network that just has been trained on how to generate realistic-looking images of people's heads. Real thing. And again, I'm not going to get into the ethics of this. We already lectured you about that earlier in the course, but this is the tech behind deepfakes, but it's also the tech behind all those viral apps you see for face swapping and aging people and making people look like Disney characters and all that stuff, right? Researchers, though, had nobler intentions for this work. Originally, some of the applications envisioned were generating synthetic data sets if you have private information. So this is especially useful in the medical field where you can't easily get real training data because of privacy laws, right? So if you're trying to generate a new neural network that can, learn how to detect breast cancer or something, it's tough to get real data for that to train it on. But by training a GAN on real data, we can sort of train it on how to make synthetic data sets that are very close to the original ones, but without any actual private information in it. So that's one practical application of GANs that is not just a viral app on your phone. It can also be used for anomaly detection. It can be used to compare an image to what it thinks an image should look like and detect anomalies automatically that way. It also has applications in self-driving cars. It also has applications in art and music. You could train a GAN on how to create an artwork in the style of Picasso or whatever your favorite artist is, or how to generate a symphony in the style of Beethoven or Mozart. And this stuff really works. You can generate synthetic art pieces and synthetic works of music using GANs that are pretty convincing. So when you see all these impressive demos of an AI that made its own symphony, This is how it works, and I think that's about to be demystified for you. It's not really as complicated as you might think. All right, so to understand how GANs actually work, you got to really noodle on this diagram here. This really sums up how it all comes together. And as you can see, it's not that hard, right? So it's pretty simple. So first of all, we don't assume Gaussian normal distributions in the latent vectors that we're learning, like VAEs. It could be anything in the case of GANs. But the thing that's really different here is that we're mapping random noise in our generator to probability distributions, or whatever they might end up being. And by doing that, by taking random noise as an input, we can generate random whatever it is as the output of this generator. So the generator learns how to take some sort of random signal and make a random face, or a random piece of music, or a random art, or a random data set, right? So that's where that randomness comes in as the input to the generator there. And on the other side, we have a discriminator that's trying to learn what's the difference between real images that I'm training the system as a whole on versus the generated images coming from the generator. Okay, so this is really the heart of it all. We have this generator that's learning how to generate whatever sorts of images or data that we're trying to create, and the discriminator's job is to detect whether those generated images can be distinguished from the real images in general, right? So you're going to be training this on a set of, in this example, images of faces. So let's give it a bunch of real face images. The discriminator is going to be learning how to tell apart those real faces from generated faces in general. And when you get to the point where the discriminator can no longer tell the difference, that's when we're done training. So you have this adversarial network going on here. The adversarial part is that the generator is an adversary to the discriminator. So the generator is trying to always fool the discriminator into thinking that the images it's creating are real. And the discriminator is trying to catch the generator in lying, right? So they're sort of in tension with each other. And that makes it a very tricky thing to train. In practice, this is a very fragile system to actually get going. But once it works really well. And that's why I'm saying that once the discriminator can no longer tell the difference between the real faces and the generated faces, or the real whatevers and the generated whatevers, we're done training, in theory, right? Because in practice, it's really hard to get this trained right. There's a ton of hyperparameters to tune. It ends up being very unstable. So an awful lot of trial and error is needed to actually train one of these things and get good results out of it. But when you take that effort, you end up with some pretty impressive stuff from GAN. So before I move on, I want to let you sort of noodle on that diagram a little bit more, because this is really the heart of understanding GANs, okay? So we have random noise that we're using that is going into a trained generator that learns how to generate fabricated whatever it is, faces in this example. We then are training the system as a whole with real faces as well. The discriminator is being trained how to distinguish the real from the fake images or data in general there. Over time, the discriminator has a harder and harder time of learning what's real and fake as the generator gets better and better at generating convincing fake images. When we get to a point, once the discriminator can no longer tell the difference, we have a really well-trained generative adversarial network going on here. Okay, so that's kind of the heart of it. We're training a generator how to generate fake data, a discriminator that is trained on how to tell the difference between real data and fake data. And when these things sort of come together, we have a generator that can generate stuff that the discriminator cannot tell the difference between from the real stuff. Okay? Fancy math, this is what it all comes down to. I'm not going to get into too much, but that is the adversarial loss function for the system as a whole. We call it a min-max game, so that is worth talking about. Again, the generator is trying to minimize its loss in creating realistic images, while the discriminator is maximizing its ability to detect fakes. So that's when we say min sub g, that's the generator minimizing its loss, and max sub d there is the discriminator maximizing its ability to detect fakes. So that's what that all means in terms of the fancy math. Like I said, it's all very complicated and delicate. The training can be very unstable. There's a lot of tuning, a lot of trial and error involved to get it to work well. And just in making the notebook that we're about to look at, took a long time to get that together and to get, halfway decent results out of it. It can also take a very long time to train, a lot of computational resources to train. But once you have it, it's a very efficient way of creating fake images of faces or whatever it is you're trying to create. Some other problems that it runs into, though, is something called mode collapse. So a problem is that, if you have different kinds of something, different kinds of faces, different kinds of pictures of shoes, whatever it is, the system can just learn how to make one of those things very efficiently and very convincingly, and that will still result in a low loss function across the system as a whole. So it's not uncommon, for example, if you're trying to train it how to create fake images of shoes, for it to only really learn how to make fake images of a sandal. And that's a problem. That's called mode collapse, where we just learn how to make one specific kind of thing really well, but it's not as general as we want it to be. It also suffers from the vanishing gradient problem a lot. We talked about that earlier in the course. And with that, let's go into some examples of seeing GANs in action, because I think it makes a lot more sense when you kind of see what it's happening in real time under the hood. And then we'll dive into a notebook and actually get hands-on with using one. So to help you understand how GANs are trained, let's look at a few hands-on interactive examples here. And after this, we'll go through a notebook to go through it in more detail. But a really nice tool for visualizing how this training works is the GAN Lab here. And let's talk about what's going on here. So instead of starting off by trying to generate fake images, let's start with something simpler, easier to wrap our heads around. Let's just choose a two-dimensional data distribution here. So what I'm going to do is try to create a GAN that learns how to create a ring. Okay, so we have this distribution of 2D points in this general ring shape here. And what we want to do is train our GAN to take a random input and randomly generate a distribution that matches that as well as possible. So in this visualization, we're going to see the real data points plotted in green. This is coming from our real distribution. And the fake ones being created by our generator will show up in purple as we train. And as the training goes on, we'll be able to visualize in a heat map the loss functions of the generator and the discriminator. So as we go, we'll see the discriminator trying to classify these points as real or fake. And what we should see is that it should eventually converge around sort of a ring shape where it identifies things in the ring as being real and things that are outside of the ring as being fake. And we can actually see over time how well the generator is doing at tricking the discriminator and how good the discriminator is doing at telling real and fake apart. So let's go ahead and kick this off. Just hit play and we can watch it in action. So you can see that our fake data here is kind of like going all over the place here at first as it starts to learn, but pretty quickly it's going to start to fall into more and more of a ring shape. And we can see our discriminator here heat map. So right now the discriminator is saying, okay, fake ones are over here, they're over here. The purple again is fake and green is real. And already we can see that we're getting sort of this ring, this circle here of white here, where it's going to start putting that green real classification around that ring and a purple fake classification everywhere else. And as we go on and on, it should get tighter and tighter. Already we're seeing the generated purple fake samples starting to get more and more within that actual distribution that came from the original real data distribution there. And let's take a look at the metrics over here. So we can see that over time, the discriminator's loss function is decreasing, but kind of holding steady because it's starting to get harder and harder to tell the two apart, right? But the generator's loss function is starting to stabilize here. Could be better. Things are getting a little bit wonky here. We can see that we've already sort of maybe hit a local minima there and kind of got a little bit unstable there, and it's kind of trying to work its way back to something better. And again, the thing with GANs is that they're very unstable. So it really takes just the right set of hyperparameters for this to work right, and a stroke of luck quite frankly, because there are some random components to the training going on here. But eventually, it does seem to be getting back to where it should be here. I think it's getting out of that and starting to get back to where it wants to be. We have kind of this weird crescent shape going on in the discriminator right now that obviously is not correct. These circular shapes are notoriously hard to learn. And those generated samples are really kind of falling into a line there, not really a circle. It was actually better earlier. Oh, wait, I think we're getting back into a better state here. All right, now we're starting to converge into something that looks a little bit better. Yeah, you can see that starting to stabilize. And we can see in the graphs here that the generator loss function is decreasing. The discriminator's loss function is starting to stabilize. Those are all pretty good signs. But again, not awesome. We can see the overall manifold of the generator here. It's not really that circle shape, but at least it's getting closer. It's kind of falling off the edge here with that distribution. And it can't really seem to get out of that in this case. So we're kind of stuck here, it seems. If we were to start it again, we'd probably get different results. So let's try it again. Now that we have a better feel of what's going on. All right, so again, the generator is got a little bit luckier this time. We're actually getting into more of that circle shape a little bit earlier on, it seems. And we can see that the loss functions are more or less stable here, because again, we kind of guessed correctly from the get-go. Still got some of those fake samples in the middle there where they shouldn't be. We'll see if that improves over time. All right, this is starting to look better. You know, that generator manifold there is looking more circular. Discriminator is, still kind of focusing on that upper right quadrant there, but overall the results aren't too bad. And now we're starting to look good. So now the discriminator is really kind of getting that circle shape and learning that, so that anything outside of that circle, it knows it's fake. And at the same time, the generator is starting to get a little bit wonky again. So again, it's unstable, right? So we're learning here that GANs are difficult to train. They can get unstable. Getting those hyperparameters and the number of epochs just right, getting the batch size just right, all critical for good performance. Why don't we try something a little bit simpler? Let's try this data distribution, which is just a straight line. That should be an easier case here, and we can see that the generator is pretty quickly converging on that line there. And we should see the discriminator starting to pick up on that as well. But already the generator is pretty close to the real data. So yeah, that's a lot easier, right? So circles are always hard, but in this case we converged on something much better, much more quickly. And you can see here that the KL divergence really shrunk quickly there. The discriminator loss and the generator loss are basically stable at this point, so I think that's about as good as it's going to get. So if you want to play with this yourself, head over to poloclub.github.io/GANLab, and you can fiddle with this yourself. There are other models here you can try and play around with different scenarios here and see what happens. All right, moving on. Taking this to another level, let's look at the GAN Playground here. Go to ryanakano.com, not sure how to say that, /gan.playground. This is actually using the old MNIST data set instead of those more synthetic data distributions. So in this case, let's go ahead and hit train here. So we're going to be training this to generate numbers, pictures and numbers. And remember, again, with the GAN, we're not training it to generate specific numbers, so I'm not expecting to see a 9 here associated with the 9 or a 6 with the 6. It's just generating numbers in general. So again, there is that mode collapse degenerate state where it just learns to make one number reliably, but hopefully we'll see something more interesting as training continues here. So what we're seeing here visually is how well the discriminator is doing at telling real and fake apart. So these are the real images coming in and the generated images as well, and how well the discriminator is doing at telling the two apart. So we can see right now we're getting 60% or so success rate on identifying real images as real. Actually, all of a sudden it's gotten a lot better. And we're identifying the fake images as fake more often than not as well. Still not great though. Obviously the visual results here are not awesome, but they are visually improving over time. So making a number is a much more complicated task than just making a circle like we were trying to do with the GAN lab before. So you'd expect this to be a little bit more computationally expensive. And we can also visualize the loss functions on the discriminator and the generator here as well. We can see that already, it's kind of struggling to get any better, but give it enough time and it will. If you want to let this run yourself for a while, after about 10 minutes or so, I find that the results get pretty interesting. And already, it's starting to look like numbers. It kind of looks like a 5 there. I don't know. Still some room for improvement, right? That kind of looks like an 8. I don't know. It's getting there, but give it more time and these will look more and more like numbers. And already I think they're kind of improving, right? So kind of looks like a 4-ish kind of a thing there, but give it enough training. And we can see that, slowly but surely that discriminator cost is decreasing. Generator, however, really struggling to improve. Now you can play around with the different, the topology of the network here if you want to, and the different hyperparameters, see if you can do a better job. But it's gonna be tough. But if you do want to play with this interactively, that's one way to do it. Let's stop this and move on to a more fun example. So this is an NVIDIA GAN demo called GoGAN, where they intentionally spelled that with GAN at the end of GoGAN, after the famous painter. And it's using a GAN to just generate fake images of different types of landscapes, right? So if I just hit the button here, it's going to automatically take this segmentation map here that I drew that says I want water down here and sky up here. And it will generate a synthetic ocean and a synthetic sky that matches with those segments that I defined. So I have to agree to the terms and conditions first. And now we should see an image like that. So they have a GAN that's trained on how to make water and one that's trained on how to make a sky, and it just kind of put them together there. It gets more interesting though. Let's actually select landscape here and put some mountains on the horizon. I feel like Bob Ross here. And you can make any kind of landscape you want this way. So not really going to be getting into any math or neural network topologies here. It's just sort of a fun example of what you can do with GANs. And we got some mountains there. Kind of a weird boundary there between mountains and water. Let's give it some ground there, some dirt. And I'll sort of make that ocean into a lake. I don't want to waste too much time on this. This isn't a painting class. But just to give you an idea of what this can do. And while we're at it, let's put some happy little clouds up there too. How about one there, one here, and one over there. And there we have our little fake landscape. So a little water hole there, surrounded by some dirt, some mountains in the background, and some clouds in the sky, all generated through GANs that were trained on how to make those different types of features in a painting at random, algorithmically. So kind of a fun example there of GANs. All right, so you've seen GANs in action. Let's go into an actual notebook and dive into how these are actually working under the hood. All right, we've had our fun, so let's go ahead and implement a generative adversarial network using a notebook here and actually see how they're running under the hood here and how to actually code one up. A surprisingly small amount of code here, so not a whole lot to go through really. They're deceivingly simple, although they're very complex to train. Now again, these are very computationally intensive things to train, so if you don't have a GPU, you probably don't want to be doing this yourself. Let's go ahead and check if we have one with this first block of code, and that will go off and load up Tensorflow, which will take a little bit, but we can see that I do have one GPU available for training. If yours says 0 and you do have an NVIDIA GPU, again, head over to this link and it will talk to you about how to install Tensorflow GPU under Anaconda. Just pip install tensorflow-gpu, but first you'll probably have to need to install some dependencies like the CUDNN library, which requires going to the NVIDIA developer website, signing up for an account there and all that stuff. But it is worth it for accelerating this training. All right, as before with the VAE sample, we're going to load up the fashion MNIST dataset, and we're going to be creating a GAN that can generate random articles of clothing. So let's go ahead and load that up from the keras.datasets package. And as before, we're going to merge together the training and testing datasets just to get more training data. Again, our goal here is not to classify data, it's to generate fake data. So there's really no use for the test dataset here. We're just going to glom it all together. And while we're at it, we'll normalize that image data from character values from 0 to 255 to floating point values between 0 and 1, because that's what sigmoid functions expect. And we will reshape the data, adding that extra dimension that we need for the CNN layers, for the convolutional layers. We'll also shuffle it and batch it up while we're at it in a batch size of 64. Oh, there's our first hyperparameter that we might want to tweak. Not much going on there. All right. So let's start by setting up our generator model. Again, this is the thing that's trying to generate fake images just given a random input. So it makes random pictures of, well, articles of clothing in our example here. All right, let's walk through what's happening here. We import the stuff we need from TensorFlow and Keras. Another hyperparameter here, how many dimensions of noise do we have? How many inputs do we have going into this thing? So we're going to start with 150 random noise values here. And we'll use that as our input. Again, you can change that and see what impact it has later on. Let's set up a sequential model in Keras, starting off with that noise vector there of 150 noise values. And we can play with what kind of distribution that noise is as well. We'll feed that into a dense layer of 7 by 7 by 256, and we'll do a transpose convolution on that in 3 layers, working up to a final image when we're done to reconstruct that. So again, this is very similar to the decoder from a VAE, right? Pretty much the same thing. So you can see how these things are very closely related. We'll print out a summary of the model just to make sure it looks right before we move on. Yep, looks sane to me. Next, we'll make our discriminator model. And again, this looks a lot like the encoder from the VAE, right? So what we're taking here as input is a 28 by 28 by 1 image, 28 by 28 pixels, 1 channel of color, grayscale. Feed that into a 256 element convolutional 2D layer, then to 128, and we'll flatten that down to a dense layer of just 64 neurons. And we'll apply a dropout phase to that to prevent overfitting. And finally output a final number of yes or no. Does this thing think that it's actually real or fake? So that's the main difference there from VAEs. You know, we're not actually trying to generate a vector of latent features here. We're just generating an output of, do I think this is a real image or do I think this is a fake image? But otherwise, pretty similar to the encoder from a VAE. Let's go ahead and hit that. Model looks correct to me. One other thing I forgot to point out, we're using the ReLU activation function here on the discriminator and the leaky ReLU activation function on the generator. And that's just something that people have learned over time that works well. Just, you know, standard best practice there. All right, let's set up our optimizers and loss functions here. So yay, more hyperparameters. So again, we have a optimizer for the generator and for the discriminator. We're calling that optimizer G and optimizer D. Both are going to be using the atom optimizer, but with different learning rates. And these are critical to get right if you want to have a stable model while you're training. If you get those wrong, it's just going to blow up. Kind of like we saw during that earlier demo of trying to learn that ring shape, if you remember back in the GAN playground. Our classifier for the loss function is pretty straightforward, though. We're just trying to figure out if things are real or fake. So binary cross entropy fits the bill for that. Similarly, for accuracy, we want to see how accurate we are at guessing yes or no, is this a real image? So binary accuracy is totally reasonable for that as well. Shift enter, we got that all set up. All right, let's tie it all together. So we'll start by defining our training for the discriminator. All right, so the batch coming in, we're going to read the shape of the data to figure out what the dimensionality of that is, what the batch size is, and then we'll create a vector of random noise that matches that batch size for the noise vector here. And we're using random.normal here for a normal distribution. Doesn't necessarily have to be a normal distribution. You could try a uniform distribution here if you wanted to as well and see what that does if you have time to play around with it. And what we're going to do next is concatenate the real and fake labels. So as we're going to see, we're going to actually stick the real and the fake data together as we feed it into the discriminator. And so we're going to have all the real data with a label of 1, followed by all the fake data with a label of 0 as we go in and define our labels here for the data that we're feeding in. That's what's going on there. We set up our gradient tape for training here. We first generate our fake data by calling the generator with that noise vector to get a set of fake images. We then concatenate that with the real data together. So we have the real data followed by the fake data. And again, that lines up with these labels of real and fake that we set up above here under y_true. We then feed that into the discriminator to see how well it does at guessing whether these are real or fake images, and then calculate the loss function that we defined above as to whether or not it got it right. All right, we have to also define the backward path for training here. We're just setting up, again, a gradient tape here, optimizer D that we set up before, apply gradients. Nothing really interesting here. It's kind of boilerplate code here, but we do pass in that discriminator loss function that we defined earlier. All right, we report the accuracy back here and keep track of that, print it out over time, and that's all there is to the discriminator model. Let's shift enter to set that up. And now let's turn our attention to the generator. So the generator's job is to not get caught by the discriminator, right? So we're going to say, we want to test how well you are at guessing that it was real. So as we go into our discriminator, we're measuring our success at whether or not it guessed that it was a real image, even though that it's fake. So that's what's at the heart of this training for the generator that's going on here. Again, we extract the batch size from the shape of the input data. We set up a noise vector that matches that batch size. And we just set up a vector of 1s because we're measuring how well we are doing at being classified as real. That's what 1 represents. So we set up our gradient tape here, and this is kind of the heart of it all here. We take that noise that we generated, pass it into the generator to create a bunch of fake images for whatever the batch size is. We take those fake images and then pass them into the discriminator. And we get back from that whether the discriminator thought those different images were real or fake. We then calculate our loss based on how well we did at making the discriminator think that our fake images were actually real ones. All right, so that's what's happening here. Not too much code really. The rest is kind of boilerplate again. We're tying together our back propagation and keeping track of the loss and accuracy over time. So Shift-Enter to set that up. All right, a little handy-dandy function here to visualize the generated images as we're going. So all this is going to do is take as an input a model. It's going to pick 81 random numbers here and pass that into whatever that model is, some sort of a generator, and visualize what it came out with in a 9x9 grid. So just a little helper function to visualize 81 random images given some model. And now let's actually do the training. So we aren't going to just use a one-line fit method here to do that. The reason is the original GAN paper actually would run multiple discriminator training steps for each generator step. But in our case here, we're going to keep it simple and just do, one discriminator training step followed by one generator training step. But if you wanted to, you could actually duplicate this discriminator training multiple times to more match what the original paper did. So it gives you some flexibility and things to experiment with again. Fundamentally, though, all we're going to do is go through 30 epochs. We're going to train the discriminator, keep track of the overall loss and accuracy, train the generator, again, keep track of our overall loss and accuracy, and just print the performance as we go. Also, for every other epoch, we're going to call that plot images helper function again to visualize 81 random sample images from our generator model. So at every second epoch, we're going to take our currently trained generator model and all the weights that it's learned so far and just visualize how good it's doing at generating fake images of clothes. So let's go ahead and set that up. And this is where the training starts. This is going to take a while, guys, but let's at least see if it kicks off successfully. Even with a GPU, this is going to be an incredibly intensive operation. All right, here we go. So here we are at epoch 0, kind of getting random blobs here at this point as would be expected. But let's wait for at least the next visualization here at epoch 2. Again, what's going on here is our generator is learning how to trick the discriminator. And the discriminator is trying to learn how to discriminate real from fake images at the same time. It's adversarial because these two things are in tension with each other. And getting that balance just right is the key to creating a generator that can create convincing fakes. All right, epoch 2 finally came back, and well, still not really recognizable, but you can see that we're getting somewhat more complex shapes out of it already. We're going to go ahead and let this run for 30 epochs and see what we end up with. It's going to take a while, so I'm just going to pause the video here and come back when it's done while my GPU heats my room. All right, about a half an hour has passed here, and my GPU has been working overtime here. It's actually hot in the office now here, so the other sort of dirty secret of deep learning is how much energy it consumes. Definitely something to be aware of and cognizant of. Let's see what happened, though. So as you can see, in epoch 0, just getting some random blobs. Epoch 2, not so much better. And by epoch 4, it's starting to do some more complicated stuff here. And starting to form into something sort of recognizable by epoch 8. These are starting to look like shirts and pants, I think. And by the time we get to 10, they're definitely starting to become recognizable. And over time, it just gets better and better and better. So even though we stopped it at 30 epochs, because, I just don't want to destroy the planet by running it further, you can see the trend here that it is, in fact, getting better and better over time. And by the time we got to 30, well, we actually stopped printing it out at 28 here, just to a vagary of the code. But even at the 29th epoch, which is really 30 because we started counting at 0, the discriminator was still only 80% effective at discriminating real from fake. So there was still room for improvement here. We could let this train even longer to get even better results if we wanted to. Very intensive to train these things. And again, they're very touchy. So, given that you have to really run these things repeatedly to tune all those hyperparameters, you can see how training a GAN can be a very time-consuming and energy-consuming proposition. But these are reasonable results. These definitely look like dresses and shirts. Well, It's mostly dresses and shirts, isn't it? We'll talk about that in a moment. Let's just take the final trained model and again just spit out 9x9 random images here to see what our final results are. And kind of points out in the comments here that it's kind of noteworthy how quickly it can generate those images once you have the trained model. So there's actually a demo on the NVIDIA website where they created a GAN that recreates a game of Pac-Man just based on analyzing the video of people playing it over and over and over again. So it can really, represent anything you want without any real knowledge of what's going on necessarily. Anyways, you can see here, these look like reasonable dresses and sweaters, I guess, but that's it. So we're seeing that mode collapse problem that we talked about before, where we're really just measuring its ability to generate pictures of clothing. And we're not measuring its ability to generate specific types of clothing, just whether or not that generator can generate an image that can fool the discriminator into thinking that it's real. So it kind of found a way to cheat here because, different types of shoes are going to be more complicated than generating a picture of a pair of pants or a shirt. And given the limited training time that we had, that's kind of what it converged on. So that's the mode collapse problem that we discussed earlier in the slides. But overall, pretty satisfying results given just 30 epochs and a pretty simple training data set there. Obviously, you can tell that there's a lot more to explore here. There's quite a gap between these results and all those face swapping apps that you see on your phone, right? So obviously there's much larger GANs out there that train for a much longer period of time that are able to generate those convincing fakes of real pictures of human faces, which is really the hardest thing to get right. But it's out there. And this is just the tip of the iceberg as far as GAN research goes. This really is sort of the cutting edge of deep learning research these days. If you look up GAN model zoos, you'll see that there's a huge variety of different models out there that you can work off of and build off of for very specific problems, and people incorporating GANs into larger systems. For example, there's something out there that will automatically generate a talking head given a picture of somebody. It can look around, its eyes can move around, it can fake talking to you and everything by sort of melding together the feature extraction of somebody's face with GANs that can create patches of that face that do different things. So lots of exciting innovation going on in this space right now. Again, I'll remind you from the ethics standpoint, please use this technology for good, and please be cognizant of the energy that it requires for training. So that's GANs, an introduction at least, enough for you to go off and learn more and be a little bit dangerous with it. Thank you for watching. If you found this video helpful, please hit the like button and subscribe to our channel, and check out the course linked to in the description. Thanks for watching.